So, me bringing to the table is the energy efficient heat exchanger technology. And today we're going to talk mainly about heat pumps. Heat pumps is like the light in the tunnel of all the problems we see. It's already, since long time, been used as a tool, a very important tool in the heating sector to reduce the CO2 emissions by replacing various other technologies emitting CO2 by something that is much more efficient, heat pumps. But nowadays, also, we want to really reduce our dependence on fossil fuels. And I would say in Germany, Europe, we talk also about reducing our dependency of Russian gas. But if we all go for heat pumps, then there will be a big need for electricity. Do we have that? I know this has to be built out. But we should see to that our heat pumps developed are efficient, so that the minimum amount of electricity is needed. In a heat pump, we are using heat that we produce from the heat pump. The heat pump is taking up heat from some waste, heat at lower temperatures, and we add the electricity. The COP is simply the factor between the heat energy we get out and the electricity we put in. Can we increase that factor? We are saving electricity. Simple. What affects heat pump efficiency? Some basics. So depending on how big difference you have from the supplies, from the heat source to the supply of heat, if that is very tall, you have higher energy consumption. So try to find the best source you need, and really question how high temperature you need out of the heat pump. Is it really needed to have that high temperature we used to with a fossil boiler? Maybe not. You can gain a lot of energy in your heat pump if you just find the exact temperature. The refrigerant type, there's a lot of refrigerants around. I'm going to come back to that, of course, to natural refrigerants. Then the system efficiency is, of course, all of us in the industry that are engineering components and systems and can make them more efficient. That I let all of us talk about. But also, not only having the difference between source and supply. If you really go above 100 degrees, we usually have the energy, the heat that we produce is going to be much more expensive and consume more energy. So, systems today are available at very high COP for temperatures below 100 degrees. And above that, of course, development is ongoing, but it will cost you more energy. Then we come to the natural refrigerants. Natural refrigerants we want to promote because of the ozone depletion since long time. But also that the global warming potential is really, really low, if anything. The cost of these refrigerants are low, means the total investment is lower. And it's, of course, a long-term solution, sustainable. And now we and many other in the industries are developing systems that are really taking down all the issues that we have from natural refrigerants, like high pressure, toxicity, or flammability. But higher efficiency can come directly from the use of the natural refrigerant itself. If you look at a heat pump where you are evaporating at 30 and delivering, condensing at around 70 degrees, ammonia, for example, can be 30% higher in COP just by using the natural refrigerant instead of a synthetic. that could pay the extra you have to spend for making an ammonia system. Alfa Laval, where I'm working, we are developing heat exchangers or plate heat exchanger types for all of the major natural refrigerants that we see used, from ammonia, carbon dioxide, propane, and the hydrocarbons of other types that's used. Plate heat exchangers are really one way of achieving high efficiency. By having a plate heat exchanger, you will have a very good possibility of increasing your evaporation temperature. This is a case for a flooded evaporator with ammonia, where we can raise the evaporation temperature on the heat source side very close. Today, quite normal to have 2 degrees, 2K approach on flooded evaporator. And this can be assured or even improved further by using a separator surge drum with that is adapted with low pressure drop, like the U-turn that we have as a system combined with our plate heat exchangers. For DX evaporators in smaller heat pumps, we are studying a lot about distribution of refrigerant in the heat exchangers. And by having a almost perfect, technically maybe it doesn't look, but it's quite perfect here, we can raise the evaporation temperature by reducing the superheat temperature. And by that, raising a couple of degrees the evaporation temperature, we can save like 10%. You can see 3 to 4% per degree Kelvin. Distribution is a way to get a high efficiency in heat exchangers. We have systems that makes a good distribution of refrigerant. This is for a condenser, over the plate rack, and also over the plate pack. In condensers, you maybe don't think that it's so important energy-wise, but it can really be. If you have a good distribution, we can do in one heat exchanger, in one stroke, so to say, have both the superheating, condensation, and subcooling, and heat the water on the other side up to the condensing temperature in one stroke. So it's possible to lower the condensing temperature down to the supply temperature. This is also a way of saving energy, for sure. Not only energy, you save also piping cost, etc., not having to have many heat exchangers in the system. This is a range. For what refrigerants do we have them then? I mentioned them, but here you have ammonia heat pump heat exchangers from all the way up to 4 megawatt, 8 megawatt heating. Depends on the delta T. Delta T 10 for evaporators, up to 4 megawatt in one heat exchanger, and up to 8 megawatt for with 20 degrees delta T for condensers. So from small capacities up to the very big one. For CO2, we have, this is mainly for smaller heat pumps, but also growing now up to some 1 megawatt with different technologies of plate heat exchangers. Of course, taking care of the higher pressure need for the condenser side. Hydrocarbon is something that is growing, and on the small size, where we are talking about 150 gram limits, we have a range of products up to the AC65, around 20 kilowatt. Or we also have double wall solution for customers that are very cautious about having intermixing. And those systems are developed with various features, assuring high distribution, and also taking care of the asymmetry between the two media, and retaining good performance. So, and then we have bigger ones for bigger capacities of hydrocarbons. Here we talk more semi-industrial heat pumps. And on the large scale, now we are talking large industrial plants. We go into industries where we are used to work with hydrocarbons since before. And we are already involved in many projects we talk more power stations, etc., with heat pumps, heat exchangers for hydrocarbons. Efficient heat exchangers does not only help your efficiency COP, it's also reducing the refrigerant charge. Here is some examples where we have ground source heat pump with propane, for example, 8 kilowatt with 150 gram. And that means that we have less than 20 gram of propane per kilowatt. This is not the most fantastic, but it's a beautiful number to see. And on the ammonia side, the case with 40 kilogram of ammonia arrived to 1 megawatt of heating. And that means around 40 gram ammonia per kilowatt. Installed, the heat exchangers need also to be maintained, especially if we are talking about a water source that is dirty. It could be a river, it could be industrial waste. It's also important to keep them clean in operation. Also here, on the water side, distribution is very important to have a self-cleaning effect on the plate. But of course, also, we can introduce maintenance plans so that we have CIP cleaning for scaling at regular times. We can measure when that is needed from temperature differences or from visual look at the heat exchanger. We also can introduce preventive filters from seawater, industrial wastewater, or backflashing valve to avoid scallops or things like that, and when flush them away before they get stuck to the heat exchanger. So you have to look at the whole life cycle. It's not only just when you sell it, it's how it's going to be used. And we try to think also all the way through. And being a member of Euremon, we will continue to drive our development and innovations for natural refrigerants, for sure. So, thanks for having me here, Alexander. If any quick questions, I still have, no? Okay, we don't have time. Okay. Oh, okay, so if you have any questions. Okay. Oh, very good. Okay.